Welcome to another OpenDSS G training session. I'm Davis Montenegro, the creator of the tool. Today I'd like to walk you through a new feature introduced in OpenDSS G version 7, the interactive voltage profile graph. This graph has been part of OpenDSS for many years, but in this release it gains expanded capabilities and interactive controls that make it far more useful and intuitive. Let's begin with the system currently on screen. The circuit includes 3 substations, each supplying its own feeder. To make them easier to work with, we'll start by identifying the feeders using energy meters placed at each substation. DSS-G simplifies this step through the Identify Feeder tool. With a single click, the tool automatically inserts an energy meter at every feeder head, giving each feeder a clear boundary. These areas can then be highlighted using the island's heat map, as shown here, making the system structure immediately visible. Each color corresponds to a distinct area of the system, which in this case means each feeder is visually separated. After solving the circuit model, I can open the interactive voltage profile graph. This graph provides immediate insight. Clicking any point reveals the node name, phase, and voltage value. And this information can be copied directly if needed. Users can also toggle individual phases on or off, making it easier to navigate the end sections of the plot. Selecting a point on the graph also highlights that location in the GUI, allowing users to connect the measurement to its position in the electrical schematic. This spatial context helps diagnose potential issues and understanding their causes more quickly. The graph additionally includes tools to identify the minimum and maximum voltage values across the entire circuit, giving users a quick sense of overall voltage performance. Users can also work in the opposite direction. They can select an area directly on the schematic and immediately display its corresponding voltages in the voltage profile graph. This two-way interaction makes it easy to move back and forth between the graphical model and the analytical view. Additional tools enhance this workflow. The Find tool lets you search for any element by class and name, automatically highlighting it both in the GUI and in the voltage profile graph. This is especially helpful in large or dense models where manual navigation becomes difficult. The graph itself is highly customizable. Users can choose from multiple visual styles, adjust the overall appearance, and enable interpolation between data points if they prefer a smoother curve. Access can be auto-scaled, and several zoom controls are available to explore specific regions of the plot, as shown in the screen. These options give users flexibility to tailor the visualization to their analysis needs. This graph also includes several export options. As shown on the screen, you can export the entire plot to Microsoft Excel and recreate or customize the visualization directly in a spreadsheet. You can also copy the plot data to the clipboard and paste it into any other application that supports tabular data. Users can open multiple voltage profile graphs at the same time, and each graph remains unchanged unless the user manually refreshes it or enables the graph's auto-update setting. Every graph is fully independent. In the example on the screen, the first graph shows the voltage profile at nominal demand. Then we increase the load multiplier to 1.5, solve the circuit again, and generate a second voltage profile. The second plot looks different because of the increased demand. With both graphs open, users can compare present and past values for the same node visually. To support this comparison, the voltage profile graphs include a sync option, which aligns the view across graphs and makes it easy to evaluate how voltage change at specific locations in the circuit. The voltage profile graph also supports an auto-update mode, which allows users to animate the plot during time series or QSDS simulations. To demonstrate this, I've configured a yearly simulation with 1-hour time steps. The simulation will advance using DSS-G real-time emulation tool, which moves the solution forward every second. After enabling auto-update and starting the simulation, you can see the graph refresh at each step, reflecting how voltage evolves over time. This feature can also be paired with other DSS-G heat maps. In this demonstration, I'm enabling the voltage heat map, which updates in sync with the voltage profile graph. Together, they show how voltages evolve across the circuit in both the schematic view and the profile plot, giving users a coordinated visual understanding of the system behavior. The concept of areas in OpenDSS G supports several visualization and analysis workflows. As noted earlier, an area corresponds to the set of elements monitored by an energy meter. In this example, the 3 energy meters placed at the heads of the 3 feeders define 3 distinct areas within the circuit. Each voltage profile graph can be scoped to any of these areas, while profile graphs default to showing the entire circuits. User can narrow the view to focus on a specific feeder or region. In this demonstration, we generate 3 separate profile graphs, one for each feeder, to display their voltage profiles individually. These graphs can refresh automatically and stay synchronized with other heat maps, creating a coordinated, interactive environment where users can observe system behavior from multiple perspectives at once. The concept of areas in OpenDSS G also incorporates a spatial context, including location and distance along the feeder. In the circuit currently displayed, we begin with a single area. By adding an additional energy meter somewhere downstream, we create a sub-area nested within the main one. Once this sub-area is defined, we can display its voltage profile separately from the overall feeder. Notice that the sub-area's profile does not begin at 0 kilometers from the substation. Instead, it reflects its actual position in the circuit, starting around 1.7 kilometers from the source. This behavior highlights a key advantage of area-based profiling. Users can not only scope voltages profiles to specific regions, but also understand where those regions sit within the larger interconnected model. With that, we've now reached the end of this lecture. I hope you enjoyed it as much as I did, and look forward to seeing you in the next session. OpenDSS G has grown into a flagship platform for exploring and showcasing the full power of OpenDSS. And for more than a decade, it has helped thousands of users learn, experiment, and innovate through an intuitive graphical experience. Each year, we push the boundaries of what a graphical interface for OpenDSS can be, bringing the engine's advanced capabilities to life with richer visualization, smarter workflows, and tools that can accelerate both research and real-world engineering. To amplify that momentum, we've introduced the OpenDSS G roadmap, a dynamic community-driven space where users can vote for upcoming features, propose new ideas, and engage directly with the development team. It is designed to make your voice central to the evolution of the platform and to ensure OpenDSS G continues to meet the needs of utilities, researchers, consultants, and innovators across the industry. As an open source project, OpenDSS G thrives on collaboration. We invite users to share their perspectives, help shape priorities, and, if interested, join as contributors to advance the next generation of graphical tools for power flow simulation based on OpenDSS. Visit opendss.prodcom.com to start your journey helping to shape the future of OpenDSS and OpenDSS G. Thank you.